So I'm going to take you through sort of how this works. And the key to the Hough transform is Hough space. Here we have a line in image space. And you all remember the very first equation you saw of a line somewhere in Mrs. Thompson's or Mrs. McGillicuddy's or whoever your Mrs. Mine was Mr. Zebro, actually. He was also the football coach. I learned algebra from the football coach in junior high school, which is a very strange thing. Anyway, so you remember that the equation of line is y equals m0x plus b0. So what we're going to construct is what's called Hough space, and it's really the Hough parameter space. And in lines, in this representation, we have two parameters, m and b. So for this line, y equals m0x plus b0, that's represented at a location in the Hough space at m0, b0. So there it is. There's the point in Hough space. A key idea here is that the line in the image corresponds to a point in Hough space. Okay, you got that? A line in the image corresponds to a point in Hough space. Now we're going to do something a little different. Suppose we only have one point in the image space, and we'll put that point here at x0, y0. Well, what are the equations of the lines that might go through that point? Well, in image space, we know that the line that goes through that point is going to satisfy, for whatever the m and the b are, it's going to satisfy the equation y0 has to equal m x0 plus b. Right? That in order for it to go through the point x0, y0, it has to have an m and b such that this equation holds. Well, with some very simple algebraic rearrangement, that becomes b is equal to minus x0m plus y0. That's the equation of a line in MB space. In fact, it's a line with slope negative x0 and intercept y0. Okay, so the idea here is that a point in image space is a line in Hough space. This is the duality. Well, if we have one point, what happens if we have a second point, x1, y1? Well, that's going to be another line, right? That's going to be a line with b equals minus x1m plus y1. And so now here's the really cool question. What line would be consistent with both points? Well, it has to be the point where these two lines in Hough space intersect, because that's the m and b that's consistent with being on a line that goes through x0, y0, and on a line that goes through m1, b1. And this, ladies and gentlemen, boys and girls, and all you interested parties, this is how we're going to find lines from points. So now we have to reduce this to an algorithm. We'll first do it graphically and then actually show the algorithm. So basically, every point gives me a line in Hough space. So what I do is I create a grid. Here it's of m and b. We're going to change that in a minute, which are made up of a set of bins. And every point votes for a line's worth of bins. So it casts a vote in every bin that it goes through. You collect up all the votes, and after every point has voted, and whichever bin has the most votes, that's your line. So this basically, we're going to be casting votes into bins and then finding the bins that have sort of a large number of votes, larger than sort of the average noisy area. Before we implement this in real code and real math, we're going to have to rethink our representation of lines just a bit. You might remember that there were some issues with the MB representation of lines. In particular, for example, a vertical line is really painful, right? Because m is equal to infinity, and in 7th or 8th grade or 9th grade or 12th grade algebra, the notion of having an infinite slope is kind of very painful. All right? So what we want to do is we want to use a more robust representation of lines so that we don't have any sort of bad numerical problems. So what we're going to use is a polar representation for lines.